Okay, so what I was trying to do here, guys, was kind of put into words the set of steps I would vocalize each time we went through one of these problems. Okay, first thing we did was write out our givens, and then we used our givens to essentially set up or identify if it was a work energy theorem problem. Once we did that, then we put in that work is a change in energy, which is force times distance. Okay, and then from our givens and the context of the question, we would determine whether potential energy was changing or kinetic energy was changing. How can we tell if the potential energy is changing? What will happen to the object if we're changing its potential energy?
It'll change in position vertically.
It'll change in position vertically. Yeah, it'll either rise or lower or fall. Okay, and then obviously if it's kinetic energy, then the object's speed is going to change. Okay, because speed is the determining factor for kinetic energy. Right? Then we set up work energy theorem by either setting work equal to the change in energy or setting force times distance equal to the change in energy. Okay? And then manipulating and solving for whatever it is we're looking for. Okay? That's the method, that's the skeleton, it's the pattern, okay, for all work energy theorem problems. Okay? So no, I don't want to do that one. Oh, it's got a weird glitch in it. Okay, well, let's try that one. It's a good inclined plane problem. What's the mechanical advantage of a ramp?
Less work is required.
Same amount of work, less force, right, is going to be required, right? Because when I get this, if I lift this mass from the ground, which I'm not going to do because I can't bend down that far, okay? But if I lift this mass from the ground, I have to exert enough force to overcome the entire force of its weight, that is, the force of gravity, okay? So on this spring scale, if I want to lift this thing, I'm going to have to exert about almost exactly 5 newtons worth of force, okay, to lift it. But to drag it up the hill, okay, requires only 3.5. Okay, and this hill is pretty steep and has a lot of friction on it. Okay, if this was a frictionless ramp, it'd be even easier. Okay, so the ramp makes the work easier. It doesn't make less work. It just reduces the amount of force. Now, there's a trade-off. Less force means more distance, right? Okay, so for this question, we got this heavy box. Okay, it's being pulled up this ramp. Man, I can't buy one today. Okay, here we go. Okay, so it's going up this ramp. Okay, we know the ramp is 25 meters long. Okay, we're just going to say that that's the mass there. It's 35 kilograms. Okay, we're using a force of 150 newtons. Okay, the distance over which that force acts is going to be 25 meters. Right? We're looking for how much higher the box is going to be at the top of the hill. Well, how high is the box at the bottom of the hill? Okay, so my initial height is 0. Okay, I'm looking for my final height. I know the mass, I know the distance, I know the force. Is this a work energy theorem problem? Yes. Okay, so if I'm following my steps, okay, on the last slide there, I've written down my givens. Now I'm writing down that work is a change in potential energy, okay, which is going to be force times distance. Okay. Now I'm going to expand that out to say that force times distance is going to equal my final potential energy minus my initial potential energy. Okay, everybody all right with that? Okay. So I'm trying to find HF. What's M times G times H initial in this question? Okay. So that just made my manipulation a heck of a lot easier. I got a lot less algebra when I can eliminate that whole thing. Okay, so how do I get HF by itself? Divide by mg, right. All right, so if I plug in my numbers then, I'm going to have 150 newtons times the length of the ramp, 25 meters, divided by 35 kilograms times 9.81. Right? That's going to give me the final height of the box, or the height of the ramp. Okay, so 150 times 25. There's how much work I'm going to do. 3,750 joules. Okay? If I divide that by the force of gravity, m times g, that should give me the height. Okay? So if I divide that by 35 times 9.81, which does need to be in brackets so it does it in the right order. Okay, I'm going to get 10 point, actually we only have 2 sig digs there, so 11 meters. Right, so that means that on this ramp, okay, I push the box 25 meters to raise it 11. But I use less force over 25 meters than it would over 11 meters. Okay, that is the mechanical advantage of a ramp. Okay, the ramp supports some of the weight of the object you're pulling or pushing. All right, questions on how that one worked? Okay, it's a pretty typical work energy theorem potential energy problem. Okay, that is ridiculously fast, but we'll go with it. Okay, give that one a try.
70.
So on this one here, okay, first step is to write down our givens, so we know the mass of the ball, and we know the force in the first line there. So, okay, mass is going to be 0.250 kilograms. Okay, the force is going to be 300 newtons. Okay, and it's over a 2.2 meter path, so that would be the distance. Okay, we're looking for the speed he will release the ball. So which V is that, VI or VF?
Yeah.
That's VF. Okay, when he's holding the ball before he pitches and he's looking at the catcher for the signal, what's the speed? 0. Right, we're changing the speed of the ball from nothing, okay, when he starts his windup, nothing, okay, to its final speed. Right, so VI would be 0. Okay, that's one of those contextual things I need to get. Okay, VF is what I'm looking for on that.
Will naturally slow down though once it gets to the mound or the plate.
We're not talking about that part.
No.
We're talking about the part where he does the work, right? Where he's exerting the 300 newtons over 2.2 meters. Because you're right, once he releases the ball, there's a bunch of other factors that are coming into play. The component of gravity, okay, that's actually going to accelerate the ball downwards. That's why it drops. Okay, air resistance, which is going to slow the ball down. If there's any spin, okay, on the ball, which makes it turn, okay, that's going to create forces. So we're not dealing with that part. Far too complex for what we're doing. We're just doing the part where he accelerates the ball. Okay, so we are looking then at work being a change in kinetic energy. Okay, that being force times distance equals 1/2 mvf squared minus 1/2 mvi squared. And as we just established, holding on to the ball while not exerting a force on it means the ball is not moving. Okay, so it has no initial kinetic energy. All right, how do I get VF by itself? Divide by 1/2 of m. Okay, that gets me VF squared. What do I want? Square root of that. Okay, so now I can plug in my numbers. Okay, 300 newtons times 2.2 meters divided by 1/2 times 0.250 kilograms. Okay, should give me the final speed of the ball. Right, in your calculator, the way I would do that is this. I'd go 300 times 2.2 and hit enter. That's the amount of work he's going to do, 660 joules. And then I would divide that by 1/2 of 250, which is 0.125, and then I would square root that. And rather than trying to worry about all the brackets and everything, that's the way I would do it. Okay, 2 significant digits, our answer should actually be 73 meters per second, which is way faster than any human can throw at 262 kilometers an hour. Okay, you would have a very hard time making contact with said pitch. By the time it was out of his hand and you reacted to the fact he'd thrown it, it would be going through the back catcher. Okay.
So, if you times by 3.6 or divide by 3.6, it turns it from kilometers down to meters.
That's the shortcut. I'll explain to you how that works another day, but yeah, that's the shortcut. Okay, questions on how that one worked? Did it still follow the same pattern? They all follow the same pattern. Once you learn the pattern, are you pretty much set on these? Really? Yeah. All right, here's one like the example we talked about the other day where you're skidding to a stop. Okay? So write this one down and give it a try. Okay? This is a very typical work energy theorem question. Okay? So, a little trick on this one. Force is a vector quantity. And if that force is causing you to slow down, then it is, by definition, backwards, and thus negative. So when we write into our givens here, okay, our force that is stopping us is negative 10,000 newtons. Okay, we are going to slow from an initial velocity of 20 meters per second to a final velocity, or speed actually, of 6 meters per second. Okay, we know the mass of the car, okay, to be 1,700 kilograms. Okay, and that's it. So, work is definitely being done, okay? And it is definitely changing the kinetic energy of the car. There's no mention of a hill or any changes in height, okay? So we're dealing with kinetic only. So that means force times distance equals 1/2 mvf squared minus 1/2 mvi squared. Okay, and I have all of these numbers except for d. So how do I get d by itself? Divide by f. Okay, so it's actually an easy algebra question, right? We don't have to square root anything. Okay, so d is going to equal 1/2 times 1,700 times 6 squared minus 1/2 times 1,700 times 20 squared, okay, divided by negative 10,000 newtons. Because the top is obviously going to be negative, this number is bigger than the number I'm subtracting it from. Okay, so we will have 0.5 times 1,700 times 6 squared, okay, minus 0.5 times 1,700 times 20 squared, okay, divided by negative 10,000, gives us 30.9 meters. We actually only have one significant digit there.
So it's 3.6.
6. So it would be, yeah, 3
to the 1.
times 10 to the 1 meters. Okay, I make every attempt to never have a question with one significant digit because it just feels wrong. Okay, but in that case it happened. Right? All right, everybody okay with how that one works? Besides the weird significant digit one. Okay, because that's a pretty typical one too, and really, that one is just testing more your understanding of the situation rather than your algebra ability. The algebra part of that is pretty simple. I'm only moving one thing. Okay. Okay, this is another very typical one. In fact, I think I put this one on a unit exam once. Give that one a try. All right, so our givens in this question, okay, are that we know the distance that the slingshot is drawn back, okay, 0.4 meters, and we know that the force used to draw it back is 1,500 newtons, so a lot, okay, and we know that it reaches a height of 30 meters. That means starting from the ground and going to a final height of 30 meters, okay, we're looking for the mass of the rock. Okay, so is work being done in this question? Yeah. Okay, what kind of energy is being changed in this question? Okay. That guy sounds boring. What kind of energy is changing?
Potential.
Potential. It's going up, right? Okay, it's talking about changes in height here. Yes, there's a change in speed too, but that's not what we're dealing with. That speed ends up, that kinetic energy ends up becoming kinetic energy in the end. Okay? Sorry, potential energy in the end. All right, so force times distance equals m times g times h final minus m times g times h initial. Since h initial is 0, what's m times g times h initial? 0, so can I get rid of that part? Okay, so I'm just manipulating for m here. What do I do with g and hf? Divide them over to the other side. Okay, so now I'm solving for mass, so that'll be 1,500 newtons. times 0.4 meters divided by 9.81 times 30. Okay, this answer would also only technically have one significant digit. Okay, 1500 times 0.4, okay, divided by 9.81 times 30. Okay, so it's only going to reach a height of 2 meters.
No.
Yeah, it weighs 2 kilograms.
Sorry, has a mass, sorry. Has a mass of 2 kilograms. Sorry. Yes, it is. Yeah, 2 kilograms. Looking for mass. Okay, not something we usually solve for. Okay, everybody all right with that one? Okay. Still pretty patterned? Is the pattern becoming pretty easy?
Yeah.
Yeah. Okay, the same thing every single time, guys. All right, I'm going to give you about a 5-minute break here, and then we'll have a look at some other ones here. All right, let's have a look at this one here. So this is just like those little carts that we had for the lab, right? They had a little spring on them that you could compress, and if you press that button, it would push off the wall. That's what that little plunger does. Okay, so the spring is compressed 0.23 meters. What did they give me there? Distance. Okay, and the cart increases in speed from 1.2 meters per second to 3.1 meters per second. Okay, and the cart has a mass of 650 grams. What does it need to be in? Kilograms. Okay, what force is needed? So work equals the change in, what kind of energy for this question? Kinetic. Okay, speed's changing. All right, so force times distance equals 1/2 mvf squared minus 1/2 mvi squared. Okay, and we are looking for the force, so all I have to do is divide by. If I want to get force by itself, divide both sides by distance, yeah. Okay, so that means then that what we're going to have is that the force will equal 1/2 times 0.65 times 3.1 squared minus 1/2 times 0.65 times 1.2 squared. Okay, and then divide that by 0.23 meters. All right, so that means we would have had to use to 2 significant digits, 12 newtons worth of force. Okay? Making some sense there? Yes? Okay. So here's how this is going to work. On your unit exam, you're going to get one of each type of work energy theorem problem. One potential, one kinetic. Important to know how they work?
Yeah.
Each one's out of 6.
That's a lot.
It is a lot, but that's what I made it out of.
That's awesome though, because then you show your work.
You show your work and you get all 6 marks, right?
Or you can get 5 out of 6 without even getting an answer.
Okay. All right.
Oh.
Okay, try that one. Asks you for 2 things, neither one of which is terribly difficult. Okay.
What'd you get?
Okay, so for this one here, it gives us first the mass in grams, so we need it in kilograms. Okay, 0.2 kilograms. And it's launched from ground level and reaches a height of 1,600 meters. What's the height at ground level?
0.
Okay, how much work is done? Okay, and how much force does its engine exert? So if I'm going to find the force and the work, what distance am I going to use? 1,600 meters. Okay, that's the distance over which the force is exerted. It just also happens to be the change in height. Unlike when you did the inclined plane, where the length of the ramp was longer than the change in height. In this case, because it's going vertically upwards, the change in height is the distance over which the force is being exerted. All right, so first thing we got to do is say that work is a change in energy because they want to know the work. Okay, we got to calculate that first. All right, so we're going to say that work equals m times g times hf, and that's it. Why am I even going to bother to write the other part? Because it's 0. Okay, so all I have to do then is go 0.2 times 9.81 times 1,600 meters. Okay, and that'll give me the amount of work being done. So 0.2 times 9.81 times 1,600 meters, okay, because that's the change in energy. So there's the work, okay, to 3 significant digits, I think. Okay, we're looking at 3.14 times 10 to the 3 joules. All right, now how much force does its engine exert? Well, this number, since it's work, equals force times distance. Okay, so if I divide it by distance, okay, what I'm really calculating is m times g, the force of gravity, right? If I'm dividing this by height, right, which is the distance in this case, so divide that by 1,600 meters. Okay, so the force exerted is 1.962 newtons. We only have 3 significant digits, so 1.96 newtons. Okay, this will be our force. Okay, everybody all right with that one? Okay, want to quickly talk about a couple of things here, guys. Just in